It's super slow when it's
Yeah, I think mine at our farm, it probably still pretty fast.
because I had to do
We never did figure out to see the last problem on the test, did we?
No.
Well, I still got a few that
Wait, where did you
haven't got it back.
the New Testament? I started learning. I used to have X-Wing, but like all my friends like me back on the PS4, and like the graphics were like actually so that's why I didn't play the PS3. Like I didn't like the graphics, so the Xbox One was great compared to PS3.
All right, we'll go over the last problem. Okay, this problem we had this is problem 4. So on this problem it was you had a ball in mass of 10 kilograms. Initially traveling at a speed of 10 meters per second in the x direction. And it collides with a 5 kilogram mass that's at rest. Okay, and then afterwards, this is before the collision. And afterwards, I'll put a little extra in the system like that. The 10 kilogram mass is moving at a 30-degree angle above the original travel direction, so it turns 30 degrees towards the y direction. So if I wanted to draw that, what would it look like? Yeah. So I have a 10 kilogram mass traveling at 30 degrees, and it says at a 4 meters per second. Like that, and then I have the 5-degree one, or the 5 kilogram mass would be going upwards.
No.
Well, that wouldn't conserve momentum, would it? Because then you'd have a net momentum in the y direction, where I didn't have anything before. So it has to be going downwards. And the idea was to figure out what this B was. So A was draw a picture of the balls before and after the collision. So before, after, that's good. That's all I wanted to see, something like that. And then B, find the velocity of the 5 kilogram one. So this one. And so what do we have at our disposal here? It's a collision, clearly. And that's pretty much all that we know. We didn't say anything about it being elastic. All we know, therefore, is that momentum is conserved. And that's true for all collisions. So the initial momentum has to equal the final momentum. And if I were to draw that, write those out, I would see that I have, I'm going to call this 10 kilograms 2m. It was 5 kilograms M. I'm doing that just because it makes things a little easier. I don't want to carry around numbers. And I'm going to call this the initial, or V1, and I'll call this velocity vector V2. Okay? So initially I have 2m V1 x hat is my momentum in the x direction, is my total momentum, right?
Mhm.
That has to equal the final momentum. So if I look at the final momentum here and write that out in vector form, I would see that this thing, which has a mass of 2m, traveling at 4 meters per second up like that, I'd have a,
Cosine.
yeah, it'd be 2. So final momentum is m v vector, whatever this is, plus 2m times v2 cosine of 30 degrees x hat plus 2m v2 sine of 30 degrees y hat. See where I got that?
Mhm.
So this is the momentum of the 10 kilogram mass afterwards. And the sum of all these has to be equal to 2m x hat. Now I can write this as m dx x hat plus m dy y hat. That's what that thing is. Plus 2m v2 cosine degrees x hat plus 2m v2 sine of 30 degrees y hat is 2m 1 hat. Notice every single term in there is proportionate, has an m. So I can divide the equation by an m. And whatever is proportional to x hat on one side has to equal whatever is proportional to x hat on the other side. Whatever is proportional to y hat on one side has to equal whatever is proportional to y hat over here. It is the vector in the x direction on each side have to be the same, and the vectors in the y, the components of the vector in the y direction have to be the same on either side. So if I look at the y direct, if I look at the x direction, I see vx plus 2 v2 cosine of 30 degrees has to equal to v1. That's one equation I get, right? I know everything on this side. Correct, except for this. And the other equation I get is that vy plus 2 v2 sine of 30 degrees has to equal 0. See that? And so I can see that Vx is equal to 2 v1 plus or minus 2 v2 cosine of 30 degrees. That's 220 meters per second, because v1 was 10 meters per second, minus 2 times 4 meters per second, so that's 8 meters per second cosine of 30 degrees, which is square root of 3 over 2. And when I evaluate that, it's 13.07 meters per second. Vy, I can see that Vy is negative 2 v2 sine of 30 degrees, right? So this is negative 2 times 4 meters per second. And then what's the sine of 30 degrees?
1/2.
It's 1/2 actually, yeah. So this is negative 4 meters per second. And so if I wanted to write the v vector, it would be 13.07 meters per second x hat minus 4 meters per second y hat. Okay. And there are many ways you could have done that. This is just one way. But that's a conservation of momentum on that one. And probably the biggest thing I saw was probably the assumption that this went off at 60 degrees. And yes, for elastic collisions, when you have the same masses of balls, yes, that would happen. For inelastic collision where the masses are different, that's not clear at all. Okay? And it probably won't happen. In fact, guaranteed it won't probably, unless you adjust them. Anyway, that's only true. The 90-degree difference is only true for elastic collisions with equal masses. Okay. If it was an inelastic collision, I couldn't have had this going up like this. If it was totally, completely inelastic where they're stuck together, because then momentum would not have been conserved.
You made a point of saying something about not specifying the
Well, any collision momentum is conserved. And so that's all we need to know. Yeah. If I said that this was a completely inelastic collision and it started out like that and started up and they were both going this way, stuck together, you automatically have a contradiction because you don't have any y component of velocity here. You don't have any y component of momentum here. Here you would have a y component of momentum if they were stuck together traveling up. You automatically can't solve it. You can't make this work. So, so that's, that would be
when you prove that.
Yeah. Okay, are you ready for the next? Ready for what are we doing? We're doing waves, right? Okay, so at the end of the day last time, we came up with kind of a formula for how to look at waves. And these are for harmonic waves that are nice and even regular waves. And the formula was that the wave, if I were to draw a wave and look at it as a function of position, you would get something that looks like this. If I were to look at the wave at one point in space, so just fix myself along like whatever's carrying the wave and just look at this point in space as the wave passes it, I would also see, I would also see some sort of up and down motion. This is as a function of time. The height here, the amplitude, and that's the same thing that you get here, of course. In time, this is called, this time it takes between two peaks is called the period of the wave. And over here, the distance between two peaks, if I took a snapshot in space, so do that single time, this is called the what?
The
Wavelength. Good. And to combine both the variation in space and the variation in time, we came up with a formula that said that the way, the distance above the unperturbed position of whatever the material is that's carrying the wave is A, the amplitude cosine, and we had 2 pi over wavelength times the position, and then if for a wave traveling in the positive x direction, it would be 2 pi over the period times the time. If it was traveling in the negative x direction, I'd have a plus there. And I could factor out a 2 pi lambda from both sides, or from here, and I get 2 pi over the wavelength times x minus or plus. And then if I'd have a wavelength over a period t. You see, if I multiply through this 2 pi over lambda times lambda over t, I just get 2 pi over t. So that's how I factored that out. This wavelength over the period was a wave speed, right? The distance over a time, wave velocity. And that's what we ended with last time. By the way, there's some terminology which you can use. This is going to be confusing when we deal with springs, or having springs and this. This 2 pi over wavelength has a special name, and when we're dealing with waves. 2 pi over the wavelength is called the wave number. And it's happily symbolized with the letter K usually, which is not the spring constant K. So you have to know from context, what you're dealing with here. Sorry, that's just the way it is.
Is that a plus or minus after the x? Right there.
Here, yeah, this is a minus or plus. So I have minus if it's in if the wave's traveling in the positive x direction, plus if the wave's traveling in the negative x direction. Also, we know that this pi over period, the angular velocity, omega, and we can see therefore that this, and that's the same thing as this wave number times this v, right? So omega is k times v. Again, not spring constant. Angular velocity wave number velocity, not spring constant in this case. Okay, so let's see if we can get some practice using this. So let's say I have a wave that obeys that equation, has an amplitude of 2 centimeters. Think of this as like that spring that we stretch out, and I make the wave go up and down along that spring. See, the wave speed is 10 meters per second. Okay. What is y at x equals 2 meters, t is equal to 1 second? Question mark. Oh yeah. And wavelength, and I created a wave so that the wavelength was maybe 1 meter. Okay, we'll start out.
When we use that equation, do our units have to be in SI units, like centimeter has to be in meters and stuff?
Well, it depends. It's good to always do that.
Okay.
It depends on what the V is. If you have See, everything in here is dimensionless. That's because I have a distance over a distance here. And this b times c is another distance, divided by another distance. So it depends on what I wanted. If this was centimeters per second, and then put seconds here, and this was in centimeters, that might be a more useful way to go. But if this was in meters per second, meters here, that'd be the more useful way to go. But so, good rule of thumb: if you convert everything to SI, you're not going to make a mistake with units. Yeah.
In that equation where you factored out the 2 pi over the wavelength, wouldn't, to change the other portion to v, wouldn't you still have the lambda over there? Because lambda doesn't fit into the velocity.
This one?
Well, below it.
This one?
Yeah, well, over by the velocity. Because you changed that to velocity, wouldn't you still have that lambda there?
No, this, so you see what I did from here? This is 2 pi. So if the time changes by 1 period. This argument changes by 2 pi. Right? So if this t was big T, I've gone a whole circle. 2 pi. So if I factor out from this whole thing a 2 pi over lambda, I want to, if I multiply this through, I want to get this term back. So 2 pi over lambda times lambda over t is just 2 pi over t, right? And so that's where that comes from. And then this is just b. Okay.
So usually, if we would know that if it's a plus or a minus by looking at the velocity, if it's
If
traveling.
it's traveling in the plus direction, oh yeah, we can, if it's
Okay.
traveling in the plus x direction, it's negative. If it's traveling in the minus x direction, it's a positive sign. You can take this as traveling in the plus x direction. Yeah. Well, it depends on where you start measuring your time from, but we'll assume that it would, our problem that it starts. Yeah, you generally have an extra phase, an extra angle there.
Is this thing we have to do with some radians?
So the going around, good question.
Yeah.
What do you guys think? Do you have to do this in radians?
Yes.
Yeah, because we've assumed here that a full wavelength changes the cosine by 2 pi, which means that we're gone all the way around in one wavelength. So that means we're dealing with radians here. So your calculator has to be in radian mode. It's going to be using this.
So you change down. What is that?
This.
A radio? We're gonna jam in here. No, it's light. It's not turning on. Oh, it's turned on.
It has to warm up for a while.
What is that? Getting that gamma rays?
think we're gonna deal with a superposition of waves, and I hope we can show off what this is like. This will probably require a little bit of work over here. Careful about figuring out where to plug these things in, actually.
Are they gonna blow up?
Is it gonna blow up?
Yeah, if you don't.
Right. That way.
Oh, cool. What is happening?
That's okay. Anyway, we'll turn off the light with this. Yeah, you guys probably won't be able to see this if I turn off the light, but. That's right. Anyway, we should go over this question in a second. All right, well, we'll figure that out in a second. What's that? Is it what?
Curious one.
Probably. Yeah, I would expect that it's not the best. Probably wouldn't want to open that up too much. Okay, so let's go through this one really quick. What do we have?
And that equation.
What's that?
Can we use that equation?
Yeah, yeah. So let's just go ahead and see what we did. So first of all, if we know what the speed is and we know what the wavelength is, wavelength is 1 meter. What's the period?
Period to
2 pi over,
2 pi over the velocity.
So E times the period, right,
yeah.
is going to be 1 wavelength.
Uh,
So that means that V is the wavelength over the period. Or let's just do solve for this. T is wavelength over V. And so this would be 1/10 of a second, right? 1 meter over 10 meters per second. We didn't really need this, but just so we know. Okay, so we can just plug in to this equation, right? So you would need 2 centimeters. Y would be 2 centimeters. Cosine 2 pi over the wave.
1 meter.
1 meter, good. Times,
2 meters.
we're interested in x equals 2 meters, I just plug in 2 meters here.
Plus.
Plus, or minus actually, if we're interested
Oh,
in
no, you just said.
positive x direction travel. Vt, which would be 10 meters per second, times 1 second. So this here, 2 meters minus 10 meters per second times 1 second, what's that?
-8.
-8 meters, yep. That's 2 centimeters cosine 2 pi. So over 1 meter times -8 meters. this meter cancels with this meter, right?
Yeah.
So this is 2 centimeters cosine of negative 16 pi.
2 centimeters.
And then what's
1.
this
One
is
estimate.
1, right?
Uh-huh.
Any cosine, any multiple of, even multiple of 2 pi is going to be 1. So cosine of 2 pi, 4 pi, 6 pi, 8 pi is 1. Negative 2 pi, negative 4 pi, negative 6 pi, etc. is also 1. So if you're in radian mode, you'll figure, yeah. Did everyone see that?
Mm-hmm.
Okay, so this is just 2 centimeters. So at that point in time, it's at the peak on the wave.
So anything with, so 8 pi, 16 pi are all gonna be 1.
Yeah.
Or you can
Cosine
just
of
plug
that.
it into your calculator.
Okay,
Yeah, just plug it into your calculator in radian mode and you'll see.
okay. So we need centimeters, not meters.
In this
I
case,
guess
you
we
didn't.
just
Well,
have
I
to
mean,
know
it's
that our
listed
impact
there,
is
yeah,
gonna
like
be
it's converted to meters and whatnot.
centimeters also.
Okay, did everyone get that? So waves kind of have an interesting property, and that is they can kind of add, well, they reflect when they get to end, and they can add together. So there's a rule for reflection I kind of want to go over. So let's say I have a string, and this is a fixed end on this wall here. And if I have a wave traveling here, this is just part of, a harmonic wave traveling in this direction. When it'll get over to this wall, still traveling. When it gets over here, what happens is that the wave actually reflects negative if it's a fixed point. So that means that if I just look at the wall, that if I have, say, a wave going like, say the string was kinked like this, right after this hits the wall, it starts reflecting off in the negative direction. Like that, okay? And the reason it does that is that if this doesn't move at all, you have the tip of the spring, the string here kind of going upwards, right? And then it's just going to go back downwards. It's just going up and down as the wave travels. And in order to conserve energy, it'll go downwards, at the same height. So the wave just inverts at a fixed point. So right after this, one more. So right after this, you have something traveling like this, so that other way around. The leading peak here was the bottom, and the leading, yeah, that's right. I had it right. That's what would happen right afterwards. It looks the same, but what happened is this thing comes in and reflects upwards and goes backwards. And so this would be looking like that. I don't know if you guys see that with your. And so the point is that waves, when they get to the wall, change from going up to down and travel in the backwards direction. So they reflect, kind of like, like something else hitting a wall, like an elastic collision, really. That's one thing about waves. The other is that I can think of two waves adding together on a string. So this gets a little bit tricky. So let's say I look at the y position as a function of time, and then and I excite a string or something that can carry a wave in such a way that this is y as a function of x, sorry. Such a way that the wave looks something like this. So let's say I have one excitation of a wave that looks like that. Let's say that in addition to exciting a wave like this, I start a little bit later and kick in something else that will excite that wave, but offset a little bit so that the wave that's excited by a second excitation is offset from the first, but has the same amplitude. Okay. And what I'm trying to do is draw it so that where the peak of one of the waves is the zero of the other wave. Okay? The rule is that if I have two waves that are excited at once down a spring or a string or whatever, that I just add those two waves together at every point in space. That's the rule for the resultant wave. So for this situation here, where I'm exciting one wave that's a little bit different, that's a little bit, this is what we call out of phase with the first wave, and this is actually quite a bit out of phase. I just would look at any point in space and then add these two waves together. So what would it be here? Here it would be, at this point I'll just draw, if I added those two waves together, it would be right there, right? If I look at this point and add these two waves together, it looks like something like this, maybe twice that height. If I look at this point in space and add these two waves together, I'm back to here, right? This point in space and add these two waves together, I'm down to here. This point in space, add these two waves together, I'm probably up to here. This point in space and add these two waves together, I'm back up here.
So it's,
Add these two waves together, I'm back to here.
so if you add them, it's just like longer both ways. I don't know.
Yeah. Yeah, so in this case, I'd get something, let me just finish kind of drawing a little bit of points and maybe we'll see it. You see where I'm getting these purple dots? I'm just adding the two waves together. So this one's this far down, each of those waves is, so I just take twice that far. Okay, this one is at a peak here and a zero here. So I'm just going to draw it. Okay. This one, oh, it should be up here, shouldn't it? This one up here again. This one here.
No, don't.
Down here, etc. And what you'll see is when you add these waves together, is you get a new type of wave called the resultant wave. Something like that. So this would be the resultant wave, or sometimes we call that the superposition of two waves. all I've done is add those two waves together. Yeah.
So those first two waves have the same wavelength.
Yeah.
The one that they make with their Foley don't have the same wavelength.
Yes. Yes, you're right. Yeah, and we'll do a couple. We'll do the same wavelength one. I don't know whether I'm actually going to get to this school light. This is. These are called interference phenomenon. When I start adding multiple waves together, this is interference of waves. These are used. These types of things are used all the time. Let's see a case where two waves can cancel out.
Like when you get pulled over and the police radio comes over your car radio. Is that
You can
basically
hear
what's
that?
happening? I've had that happen before.
What?
I didn't know that even could happen. It's probably just your car radio
Picking up their radio.
Oh yeah, I've heard people do that. I haven't either.
Like radio in the other car?
Yeah,
Really?
yeah.
It actually messed with the TV too, because the cop followed me home because I was 14 and driving without a license. And the TV messed up, and my mom was looking around. And I could see her in the window. I was like, "Oh, this is gonna be rough."
Yeah, then all your stories are pretty good.
Yeah.
All right, let's go ahead and look at these ones. Let's say I have two waves that are exactly half of the wavelength out of phase. So this is half of a wavelength out of phase. The peaks of one correspond to the troughs of the other, and vice versa. If I were to add those two waves up, you could see that any point here, I'd want to add these two things together, and they're negatives of each other, right? So if I added those 2 points up, I'd always get a dot there. Same thing here. These two waves, if they're the same amplitude, 0 here, 0, 0, 0, clearly 0 all the way along. The resultant wave of adding these two waves, nothing, right? This is called destructive interference.
What's that one called?
This one's kind of somewhere in between.
It's not called.
It's just an interference. It's not either completely constructive or completely
So-
destructive.
How far apart were they?
Well, do you see how this is half of a wavelength apart?
Uh-huh.
So where the peak of one is, the trough of the other is, and vice versa, same amplitude. When that happens, you get what's called destructive interference. The wave disappears. You don't have anything going on there. And this could happen at a point in space or a point in time, or over all points in space. You just have waves destroy each other. So it's kind of interesting. I mean, so that thing's kind of interesting. As an example of this, I wanted to show these string node things. I don't have a good way to hold this up. Does somebody want to try and hold this and maintain see if you can maintain kind of a constant pressure. Okay, now loosen it until we start to see waves. Okay, see those?
Yeah.
You're doing pretty good keeping that steady. Now, you see how these waves are, over here they're moving up and down, over here they're not. What we have here is we're exciting a wave here. The wave travels through here, reflects off his hand, upside down, and then comes back. It just so happens that at these points, that all waves will add together and they will. These are called nodes. The reflected wave and the incoming wave add together at these points in such a way that the wave disappears. Okay, that makes sense? And these are antinodes. They add together in such a way at these points, the reflected wave and the incoming wave, that they get, that it increases its size. Let's see if we can, maybe we can set it up. I wonder if we can do it like this. Yeah, you can do it like this. And if, by the way, I wanted to, alright, this ain't working. I'll hold this up. Can you put that mask on it? Yeah, we're getting you guys see that? See how some of like at this point, the wave isn't moving. The wave, the reflected wave and the incoming wave disappeared. Yeah. You know what? We'll what I wanted to do, if you guys can see this real quick, maybe we can figure this out. What's going on later? I want to turn off the lights a little bit just so you guys can see what's going on. Turn on. Okay, we'll turn on that. Oh, by the way, can you guys see what's going on?
Yeah. Oh,
Wait,
cool.
But when the lights are on, it didn't look like that, right? It
No.
was straight.
Yeah.
No, it's not straight. It was, you saw the vibrating waves, right? You see what's going on?
Yeah.
And if I adjust this a little bit, the speed of this, and it goes all crazy. Okay, what I'm doing with this thing is I'm actually flashing the light at various times, and if I get it so that I'm flashing the light at the frequency of the wave or near it, I can, I'm only looking at the wave once every period. And if that's the case, then the wave looks the same, and I can get, kind of makes it look like it's a still thing. Can you get it so that and I don't know if you guys can see it, but feel free to leave and come over and look at this as you read it. You can adjust it so that you get it moving very slowly. That's the next thing we'll deal with. That's an example.
It's what?
Let's set this up so you can maintain the lead.
Yeah, like,
You're doing a pretty good job, Alan.
I want to
Yeah. If we were